Welcome back, my statics friends. Up to this point, we've been studying centroids and how to find centers of area and centers of mass and things like that. But we also need to consider, is there a way that I can use centroid calculations to handle more complex forces? In this video, I'm going to show you how to do it. So without further ado, let's get started. If you recall, a couple of videos ago, we were doing summation calculations for centroids. Okay, we've also done some integration calculations as well. And the method for resolving forces is very similar to both of those. So I'm going to walk you through kind of the process. Let's review a little bit in case you haven't seen the previous video, but it's also good practice just to reinforce what we've been looking at in recent classes, is that we had a summation notation that we established for finding a centroid position x bar. Okay, now we're looking at the center of area formulation that we've been kind of centering our discussions around the last couple of videos or so. And in this calculation, x bar is equal to the summation of I equals 1 to n of xi ai all over the sum of I equals 1 to n all over the ai. And again, I is just an index counter and has to do with the number of regions that you divide an area up into. So here I have a shape that consists of a semicircle and a square, so I would have two regions. And so if I were to come in and kind of write my formulas for this, recall the summation notation is sum of I equals 1 to n of ai is a1 plus a2 plus a3 all the way out to an, and that all of those added together is simply a total. Okay, so for our case with I equals to 2, we had a summation of I equals 1 to 2 of ai is equal to a1 plus a2, and that's my a total for my region. Okay, and then likewise, we can do the denominator or the numerator of this portion in a similar way. So the equation we just did was the denominator. This numerator then looks like, the summation of I equals 1 to 2 of xi ai is now going to be equal to x1 plus a1 plus x2 plus times a2 is that quantity. Okay, now again, I wrote it generically all the way out to n, but in reality, my n only goes to here. Okay, so it's x of 2. Now, how do we kind of apply this? So let's take a look and suppose that I have a shape that looks something kind of like the following. Maybe I have a region in which I'm looking at 6 inches in this direction and 4 inches in this way, and we'll put a 3 inches up here. Let's see if we can figure out how to calculate our quantity. So all we do is we basically break this up into regions that I can work with. And so this is a rectangular shape at 6 on the bottom, 4 on the top. Again, I'm setting my reference for both the x and the y direction at the lower left corner, and I do that to give me a positive value on these centroid dimensions. You can put it anywhere you want because these calculations are all measured back to whatever you choose. So I could choose, over here or down here or even out in the parking lot. As long as I know where that point is, I can locate this point in space. All right, but if we go look at a rectangle and I make this my lower left and that's my reference, then the centroid of this is clearly half of 6 or 3 inches for the x1 dimension, and then half of 4 or 2 for for the y2 dimension or y1 dimension. Oh, sorry about that. Bit of a frog in my throat. Let's try that again. So y1 is going to be half of the height to get me the centroid of this. So what we're doing is we're locating these points. Okay, and then I know how to find the area total of this is just 4 times 6. So that's all my data here in the bottom. Okay, so x1 is 3, y1 is 2, and then my area 1 is 4 times 6 or 24 square inches. Okay, now we can do the same thing, and I use the exact same reference system. I can do the triangle, and so notice my 0, 0 is down here. It's not even on the object now, and that's fine. It doesn't matter. Okay, the base of the triangle is 6 inches horizontal, and it's 3 inches high, and it's offset a distance of 4 inches. Okay, but the only area I'm calculating is what's being shaded here. All right, so if you remember a triangle, it's 1/3 of the base from the high end. Well, my high end is on the right here, so I'm going to do 1/3 of 6 inches. That will be a 2-inch dimension. Okay, will get me that one, and then my x2 is whatever is left, and so again, we have to measure our x value from my centroid reference. Okay, so even though I know that the x bar for a triangle is from the high end, this number, okay, I've got to shift that and make x2 as being 6 inches minus 2 or 4 in this because of the orientation of the triangle. And that's what you see I've done down here. Okay, so you got to kind of watch the orientation, which way this thing is aligned and so forth and so on. Okay, now the height is 1/3 of 3 inches from the high end, and the high end in the height is the bottom edge. That's by high end, I mean the largest of that edge. So 1/3 of 3 inches is 1 inch. Okay, and so then my y2 dimension for this particular shape is going to be the offset 4 inches plus 1/3 of 3 inches or 5 inches total. Okay, and so that's how you find the centroid positions of this shape in space. Okay, A2 is then the area of the shaded region, area of a triangle, 1/2 base times height, so it's 1/2 6 times 3, 9 inches squared. And that will get us those. So now all you would do is you plug in these regions, okay, and we can get ourselves set here. Okay. A little bit of some blurring is happening there. Sorry about that. All right, let's try this again. Okay, so if I go through and I look at this, then all I'm going to do is we're going to make our familiar table that we did back in the video, a couple videos back. Now, if you don't remember this, go back and watch the centroids by summation, and we'll talk about what cells to use in this. Okay, but in a nutshell, here it is. My region, I have I equals 1, I equals 2. 1 is the square, 2 is the triangle. AI is the A1, A2 values that we chose before. So A1 is 24, A2 is 9. That's these two values. XI is the centroid of each of the I elements. So X1 is 3 inches. That's this guy. X2 is 4 inches. That's this one. And then YI is for the Y direction, 2 and 5. So that's what we have happening here. And now all I do is I just multiply these columns together. So XI, AI is what's happening here. So I get 72 and 36. And YI, AI is 48 and 45. Again, going fairly quickly through this because we've done this in previous videos. The only other thing I need to do now is do summations, and the sum of the areas is 24 plus 9 is 33, and the sum of XIAI is 72 plus 36 or 108, and the YIAI is 48 plus 45 or 93. Now again, units are as indicated, inches cubed, inches squared on those. And so then to find the centroid of this area, then I just plug into my formula. X bar is the sum of XIAI over sum of AI. So for the X direction, I take the 108, divide by 33. That number is 3.27 inches. And then my Y bar, I do the YIAI summation all over sum of AI. 93 over 33 is going to be 2.82. And so those are your dimensions to the centroid of this as measured from my original reference. So if this is my combined shape, then the centroid of this area is 2.82 up from the bottom. That's my Y bar dimension. Okay, and then in the horizontal direction, it's 3.8. I said 3.8, it should be 3.27. Okay, there, and that's my X bar value. Okay, so it's just exactly what we were doing back in our centroids by summation technique. Okay, now, let's go kind of try to consider what are we going to do with forces. All right. Up to this point, what we've done with forces is we've been handling concentrated effects, okay? And whether it's a force or a moment, okay? What we know that there are a lot more load cases out there that are more than just concentrated forces. So what about the others? How do we handle those? Okay, imagine it's snow on the roof of your house, right? If snow comes down and it's kind of a uniform load that's applied over a certain length. Well, you could model that as a uniform distributed load, which is what this guy is. Okay, and so if we look at how do we handle this, we're going to use our equivalence techniques to kind of try to employ this, so that we know that if I create equivalent systems, then I should be able to, whatever the rules are, even if we didn't know it, I should be able to generate a set of relationships that will relate this system here to an equivalent system consisting of a single force at a single point. So this is your single force resultant happening here. Okay, now if we look at this one's simple enough that it's a simply supported span. I said, let's say L is 20 feet. Okay, and so if I have 10 pounds per foot over a length of 20 feet, we know that I have 200 pounds per foot, 200 pounds total acting on this beam. It's the length times that 10. Okay, and if this is uniform, then each support is going to carry the same amount. Well, it turns out that that amount is WL divided by 2. Okay, So 200 pounds is the total, half goes to this support is 100, and then same half over to this one, 100. Okay, so the total force of the load acting down on this thing is going to be 200 pounds. Okay, and again, that's just the area of the load. Okay, as well, if you start looking at that, well, when we were doing areas of multiple regions, like we did in the last example, well, that was kind of this calculation, wasn't it? A1. And how did I find A1? It was the area of the area. Well, now we're doing the area of the loading region for the force. Okay, and so that's all we've done. So far we're still kind of on track with what we're trying to get done. Now, for this system to be equivalent to this, I want to apply a single force somewhere on the beam. Okay, at a position of x bar. Now, what we've done is, again, we've set the reference relative to the left side. You can choose it anywhere as long as you're consistent. That's fine. But my x bar in this is an unknown. We don't know where this force is applied, but I do know its value now because I got it over here. All right, so when we were doing equivalence of areas, this resultant force was the total force happening on this thing. Well, now I also know that the support conditions in this have to be exactly the same as this one in order for the systems to be the same. So all I'm going to do is I'm going to do sum of forces in the y equal to 0. Okay, and say you didn't recognize that this was F total. Say you didn't recognize that this was the total. Well, we could come in and we could say, well, if the equivalent support reactions were the same, you know, maybe this is AY and this is BY, well then I could solve for the F total that makes this true. Okay, and in this case, F total is just going to be this reaction plus this reaction. So 100 plus 100 minus F total equals 0. We could apply equilibrium on this, and so F total is 200 indeed. So those two match up. And we said that was simply W times L for this particular load case. All right. Now, the position comes about as a result of our moment equation. So all I'm going to do is I'm going to choose some moments at one point. So I'm just going to, for the sake of argument, just going to choose the left end. Okay, and I'm going to find the moment of all of these forces on this diagram. So the first one I have is 100 pounds times 0. Okay, don't really care about the direction. I have 100 pounds times 20 feet. And if I assume counterclockwise positive, that's a positive 100 pounds times L. All right, and then minus my F total force times its distance x bar happening up there. And then all of this better sum to 0 if we have our equilibrium in place. So let's look at what we've just done here. If I write this out a little bit differently, 100 pounds times 0 plus 100 times L equals F total times x bar on this. Well, this 100 pounds was a WL over 2. And the 0 was a dimension from my point that I was interested in up here to the force. And so because this force was at my point, X, and this was a 0 dimension, well, that's an F1 X1 quantity. Okay, and if I come and I look at the next term, I now have another WL over 2 multiplied by its distance from my reference point of L. Okay, well, that's this force multiplied by its distance of L. Well, that's X2. All right, and so this was F2 and this is X2. And so what we have is something that kind of looks like that. Okay, and if this whole thing adds up to be F total times X, where F total is WL on this times X bar, then I kind of have this before and after thing happening on the beam, but I can solve this equation for X bar. And so X bar is going to be F1 X1 plus F2 X2 all over F total. And if I add more forces, I just add more terms, but it's still the same approach. And I can write this as a summation notation of summation of I equals 1 to 2 of xi fi, okay, all over the summation of I equals 1 to 2 of fi. Okay, except for what we've done is we've said that I have these two discrete forces, force number 1, force number 2, that we're dealing with on that guy. All right. Okay, and so if I go through and I plug in my math, then I have 0 plus 100L all over 200 is going to be equal to L over 2. Gets me the location of X bar. And so what that means is that in my picture, for a uniform distributed load, X bar on this case is going to be equal to L over 2. Okay, and now you've got the force of 200 pounds located at a distance of L over 2, which in our case would be 1/2 of 20 feet or 10 feet. It's in the middle, which is what we had when we had a rectangle kind of calculation. So you've proven it for forces. So really what it boils down to is that the centroids of forces are very similar to centers of area. This is kind of a rectangular load, right? Well, the center of a rectangular load is in the middle. Okay, L over 2 from each side. It's the same idea, okay, except now we're doing it for forces, doing the exact same approach for what we've been doing. So let's try a little bit more complex one. Okay, what do you do for a load that isn't the full length of the beam? Okay, let's see if we can find the reactions for this beam. I've got a beam that's A to B. It has a distributed load of 5 pounds per foot for a total of 3 feet. And then I have a 7-foot span that has no load on it that gets me over to B. And I have, it's simply supported, roller here, pin here, and we're good. And I want to basically find the reactions. Well, what are we going to do? We're going to draw the equivalent system and try to solve for AY and BY. So again, since we don't know what X bar is, on its own right on the beam, we can come in and I can draw this. And again, I like to draw these, the original load is kind of a dotted shape to recognize that I've converted it. Okay, let's just say that this is now at a distance X bar. We have an F total. That's the load acting down. And then I have a reaction AY and a reaction BY. And the length between these is 10 feet. Okay, and of course you have a reaction BX on there. All right, well, let's go with what we know. We have a distributed load, and the first thing we had to do was come up with the total of that distributed load. Well, that was 5 pounds per foot times 3 feet, or 15 pounds. So that value is 15 pounds. And it was located, according to our original picture, at the center of the area of the load. Okay, so for us, our X bar of this load is going to be equal to 1/2 of this 3-foot dimension. And that puts me at the center of this point. Again, it's not the half of the full length of the beam, it's a half of the dimension on the load. Okay, and so that gets me 1.5 feet here. Okay, and so then if I go through, now we've got our values on this, I can now come in and just write my equilibrium equations. Okay, because we now have a valid free body diagram. Okay, so if I do sum of forces in the X, the only thing in the X is BX, so BX is equal to 0. There's the first one. Okay, I can also come in and do sum of forces in the Y direction equals 0, and so that's going to be, if I assume up positive, it's going to be plus AY plus BY minus F total. That's exactly what we've written here, all equal to 0. So AY plus BY is equal to 15 pounds. Okay, and I can't do much with this at this point because I have 2 unknowns, but I could write one in terms of the other. I could say AY is 15 pounds minus BY if I wanted, just like you could write BY is the same thing. Okay, so if we look now, let's go through and let's apply our moment equation. And again, just for reference, I'm going to choose to do it at the left. You can choose any point you want. Normally you would do it at one of the supports. Probably would be better to do it at B, but again, it doesn't matter in this problem. Okay, but if I do summation, the moments at A, counterclockwise positive, all equal to 0 on this picture, okay, what do you have? Well, you have AY times 0, okay, plus BY times L, okay, minus F total times X bar. Okay, that's the equation that we just wrote here. So where my L is 3 foot plus 7 foot or 10 foot. Okay, and so the AY vanishes. I can solve for BY then as being F total times X bar all divided by 10. If I take this and kind of rearrange it and solve for BY, and then I plug in my values, F total is 15 pounds. Okay, and then my X bar is 1.5 feet. Okay, and we're going to divide that by 10. It gives me a value of 2.25 pounds acting up on the reaction at BY. And then once I have BY, I can then go back to my summation in the force of the Y direction and do 15 pounds minus that BY value, or 12.75 pounds, also acting up. It's a positive value, so it matches what I drew my picture at. And so that would be my value for AY, 12.75 pounds upward. And with that, you have all of the reactions done. Okay, and here's the last line so that you can see it. Pretty easy, pretty straightforward, but it's just using equivalence. So now we're really getting into being able to do some heavier analysis, handling a lot more complex loadings. We're no longer limited to just doing concentrated forces. We can now look at doing distributed forces. Okay, but what if you have a load that's not a simple rectangle? Well, what do? Well, by now you've probably got some idea. For more complex loadings, okay, my centroids by integration also work. Okay, so let's suppose that I have a beam that is a cantilever with a reaction all right, sorry about that. That's what happens when a cat jumps on your desk when you're recording. So if you saw the camera fall over, so maybe make that a bonus question on the next quiz. What happened during video number ENGR212 or whatever it is that we're on. Okay, so anyway, for those of you that are watching, make a note of it. Okay, so anyway, for more complex loadings, maybe I have a distributed load that's just some arbitrary pattern, but if I can write it as a function of x on this, so it could be, you know, I draw it as kind of this wavy thing that's non-constant on this, but the w function can be anything, okay, and all we would do is, you know, even for a loading that wasn't simply supported, you know, at the end of the day, as long as, you know, say it's a cantilever, you know, like a diving board kind of problem. I have a pin here and a roller here, reaction of AY, reaction of BY, you know, technically you would have an AX that happens here, and an AX that happens there, okay? Assuming that the equivalent system is the same as the original on here, well then I should be able to, if equivalence is true, then I should be able to write that this whole complex load is the same as a single load applied at some centroid location that we would call as kind of an x bar kind of thing. And that's, I do that as x squiggle, that should be x bar. Now, if you remember our notation, we said that what we did with integration methods is we slice our area into pieces. Okay, so that's this little shaded chunk. Okay, it's going to have a width of dx. Okay, its centroid is this x squiggle kind of thing. That's a technical engineering term there, x squiggle, but it distinguishes it from x bar, which was the resultant of the total on those. And so by the logic that we had with areas, well then we should be able to do x bar is the integral over the entire force region, which was x squiggle times df, all over the integral over the force region of each of the little df pieces. We're basically integrating and finding areas onto this. Okay, well, what is df? df is simply my w as a function of x this way. Now again, this isn't w times x, this is just w as a function of x, okay, and multiplied by the width of the piece. So the height of the function is wx, and the width is dx, so that's what I'm writing here. Now, just to keep ourselves clear that this isn't an extra x running around, I'm going to start writing it like this, w dot dx. Okay, and then the centroid of this region, if my reference is the left, then the centroid to the center of the area is the same as my random variable x. And so that's what we have happening there. Okay, so then all I have to do is we've converted from an integral over a force region into now a linear integral in dx. All I have to do is do x bar is equal to the integral from the left end, L2 plus L1, to 0, basically the entire distance under the load on this, okay, of x times w dot dx all over the integral of the total area, or total force on this, which is integral of L2 plus L1 over 0 times w dot dx. Again, this is just the total force, okay, and of course we said that where w is w of x, a function of x, okay, and so it's the exact same approach that you saw as we start to kind of set this one up. Now again, I didn't work out all of the algebra for this, we didn't really define w as a function, but that's the way that you set this up. It's exactly like the integration method. So if you're struggling with that, go take a look back at our last video and we've kind of walked you through in some more detail how you set this up. It's exactly the same approach. But now I've got the ability to handle not just uniform loads, but I can handle any load as long as I can define the load as a function of x. Okay, now some of the more common ones that you'll see in mechanical and civil engineering and structures will be a distributed load over a length of L. We talked about this one, that the resultant of this load is W times L, and it's located at the center of the difference. Now again, I'm doing a reference here, so put that on there, and so my X bar is L over 2. We proved that one for you a little bit earlier in this video, okay? But what about a triangle one? Okay, now we've talked about triangle shapes. We know that it was 1/3 from the high end. Well, if I come back and look, well, I know that I can take a distributed load that looks like this with a triangle that is increasing to W naught on the right end over a length of L, okay? And so we know that it's 1/3 from the high end, okay? Well, if I set my reference at the left, that x1 bar dimension is L over 3. There's the 1/3 high end dimension. But say I chose to do it off of the left end and I called that as reference number 2. Well, then my x bar 2 of this guy is going to be equal to 2L over 3. It's 2/3 of L, because it's 1/3 on this side, then if the whole thing is L, that's got to be 2/3. Okay, and then the resultant force itself is just the area of my triangle, which is going to be 1/2. If the height of this load is W naught at the high point, okay, and the base is L long, then the area of this is 1/2 W naught times L. And you now have the ability to handle triangular loads very quickly. Now, again, you've got to be careful on the direction, because if I have a triangle load that's going the other direction, your X bar dimensions will flip, because now the centroid is 1/3 from the left, not 1/3 from the right. So the triangles are the tricky ones. You got to kind of watch those. Okay, but at the end of the day, it's the same values as what you were seeing with the centroids of area. So if we did quarter circles or semicircle loads, or whatever the case may be, you can always go look these up in tables such as the ones in the front of your book, your statics book. Our class, we use the Beer and Johnson text. They have those in the front, but most statics books have something like this table in them anyway. Or if you've got another resource that has them, feel free to use that. But just make note of where they're measuring from and where my centroid is located for all of these complex shapes. So anyway, I hope that's made sense to you. It's a fairly quick one, but it's so powerful, because now we can start to leave distributed or leave concentrated effects behind us, and we can handle any kind of loading. I can always have concentrated effects, and I just add the picture to this, and it's just another, X1, F1 term that shows up in this thing. But the approach is very similar, but it's just a little bit different. And so I wanted to kind of take some time and kind of walk through that, because I think it was worthwhile. So anyway, I hope that's been clear to you. If you got any questions, as always, leave us some comments down below, and I'll be happy to try to resolve any issues. Enjoy the cat jumping up on the desk. That was fun, right? And we will see you guys in the next video. Remember to toss us a like on the video, and be sure to subscribe to the channel, and we will see you all next time. Happy engineering.